Neotec, negative emissions ocean thermal energy conversion, a planetary energy and environmental silver bullet. Carbon dioxide, CO2, and water, H2O, combine to produce carbonic acid, H2CO3. 90% of the Earth's crust is composed of carbonate or silica minerals, which are eroded by carbonic acid over millions of years to produce beach sand, silicon dioxide, hydrogen, oxygen, and acid. Crushed rock erosion by carbonic acid can be an overnight process in the presence of an electrical charge. Neotec is an excellent way to produce electricity. In turn, electrolysis is an excellent way to produce the energy and water carrier hydrogen. Increasing CO2 levels warm the oceans. Over 90% of the heat of global warming has been absorbed by the ocean. About two-thirds of this within the upper few 100 meters of the surface. The temperature of the ocean's surface can be as high as 36 degrees Celsius. The average temperature below the ocean thermocline is about 4 degrees Celsius. 90% of the total volume of the ocean is found below the thermocline. These temperature differences lend themselves to the production of work in a heat engine. Carbonic acid and ocean heat are detrimental to marine organisms. Increasing ocean heat leads to sea level rise, increased ocean heat loading, and storm surge. This is a flyover of a proposed Neotec plant that sequesters ocean heat and carbon dioxide and produces negative emissions hydrogen. The heat pipe and condenser are on the surface for transportation and/or maintenance. This is an underwater view of such a plant. Each subsurface pump produces about 1.5 cubic meters per second of surface water. Each island array consists of 195 pumps, which are estimated to be able to produce 1 megawatt of power. A turning impeller provides direction. The island consists of 392 solar panels of 8 by 16 meters, or about 42 times the size of a conventional unit, with an estimated combined output of about 4 megawatts. The main body of the plant ship incorporates a water-holding tank, a desalinator, hydrogen tanks, turbines, evaporator tubes, and side loading for minerals. Anodes and cathodes produce oxygen and/or chlorine and hydrogen. Seawater mixes with magnesium silicate to produce magnesium hydroxide. Conventional Neotec is modified to produce surface ocean cooling without the vertical movement of water. The system is further modified to negative emissions ocean thermal energy conversion, Neotec, which converts renewable energy to negative emissions energy. Oxygen and/or chlorine from the anode is gathered for the prevention of biofouling. Surface water is collected in a pipe which is covered by a marine life screen, which is mated to the island. The surface water is then pumped into a holding tank. 4 cubic meters per second of surface water is required for each megawatt of Neotec power. The warm water flows through the piping of a heat exchanger into a collector, where it is forced out by an impeller. This is a rear view of the warm water system. This is an overview of the warm water system. A dissection of the evaporator reveals the tubing and a main header and a fluid inlet. The working fluid is warmed by the surface water flowing through the piping to produce a vapor. The vapor is collected in the upper portion of the evaporator and goes out through an outlet. The vapor then flows through a turbine to produce mechanical energy, which is then converted by a generator into electrical energy. The spent vapor after leaving the turbine is then collected and sent through a ball joint to a depth of 1,000 meters. The pipe can be constructed in 10-meter long sections. This is the underside of the piping, and a side view of the harness connecting the plant ship with the ball joint. Tensioning cables connect the surface and deep water sections of the system. Markers indicate the depth as the vapor descends. Pressure increases on the heat pipe with depth. Carbon dioxide as a working fluid helps to equalize the external pressure acting on the heat pipe. This is the top view of the deep water condenser. A dive plane helps to keep the condenser at the operational depth of 1,000 meters. This is a side view of the condensers. Ballast is required to keep the condenser down. The buoyancy of the condensers in the heat pipe is maintained at a negative value. The working fluid is then directed into the condenser. A dissection of the condenser shows the vapor inlet, the vapor, the condensing working fluid, and the exchanger pipes through which 4 degrees Celsius water flows to bring about condensation. The fluid then returns to the surface. A series of pumps may be required to return the condensed working fluid back to the surface. At the surface, the turbine is connected to a generator for the production of electricity. The red wire directs the DC voltage to a cathode. The blue wire directs the voltage to an anode. The plant specifications are 1,200 meters of 1 meter diameter collecting pipe, servicing 12 evaporators with 1,200 cubic meters of warm water per second to produce 300 megawatts of electrical energy from 6 turbines. 600 cubic meters per second of cold water condenses the working fluid. The parasitic losses from pumping are estimated at 15% of the net 250 megawatts of power. Energy cost is estimated at 20 cents per kilowatt, which equates to hydrogen production costs of roughly $14 per kilogram. While this is higher by twice the cost of land-based hydrogen production, this does not account for the price of the CO2 avoided, the surface heat sequestered, or the sea level reduction benefit. At a length of about 300 meters for a hull, a beam of 75 meters and 600,000 deadweight tons, it is comparable in size to the largest oil tankers. At about $1.8 billion, it would be comparable in cost to a small modular nuclear reactor. Without the proliferation or environmental risks and better sea level, heat, and biological outcomes. Such systems can usher in a new dawn in sustainable energy.